Mixture separations in fixed beds packed with morphs or zeolites are determined by three separate parameters. The most important one is the adsorption selectivity, determined from the thermodynamics of mixture adsorption. The second one is the severity of diffusional limitations, where D sub I is the intra-crystalline diffusivity of the guest component I, and R sub C is the radius of the crystallites of morphs or zeolites. If the ratio D sub I divided by RC squared is very large, there are no diffusional influences, and the separations are dictated primarily by the adsorption equilibrium. In addition, we have a third parameter, which is the ratio of the guest diffusivity within the pores for component 1 divided by the corresponding guest diffusivity for component 2. Let's call that the diffusion selectivity. We can identify two scenarios where for components 1 and 2, both the adsorption selectivity and the diffusion selectivity are greater than unity, and we have synergy between adsorption and diffusion. Another scenario is one in which the adsorption selectivity is greater than unity, but the diffusion selectivity is significantly lower than unity, and this diffusion selectivity serves to override the adsorption selectivity, and we have antisynergy. All these discussions are based on my paper published in Precision Chemistry and online in 2023. Let's pick up some of the highlights from my paper in the subsequent slides. I present here 4 sets of experimental data on transient uptake of binary mixtures inside 4 different adsorbents. On the left here, we have the uptake of normal hexane and 2-methylpentane inside MFI zeolite, and we note that during transient uptake, the component loading of normal hexane shows a pronounced overshoot, and at equilibrium, the molar loading of normal hexane is higher than that of 2-methylpentane. The ratio of diffusivities of normal hexane to that of normal 2-methylpentane is 100, and both adsorption and diffusion favors normal hexane. So this is an example of synergistic separation of normal hexane and 2-methylpentane using MFI zeolite. Here is another example of a synergistic adsorption diffusion phenomena observed for mixtures of ethanol, shown by the red circles, and the blue squares represent 1-propanol. Both adsorption and diffusion favor ethanol in SAPO 34, which has the same structural topology as Shabasite zeolite. We again note a transient overshoot in the uptake of the more mobile component, in this case ethanol. Here are two examples of experimental data for antisynergistic separations. In this case here we have separations of equimolar mixtures of nitrogen and methane in LTA4A zeolite. The uptake of nitrogen shows a pronounced overshoot, whereas the uptake of the more strongly adsorbed methane, which is the tardier guest, shows no overshoot. Here is an example of uptake of mixtures of carbon dioxide and ethane in DDR zeolite. The mixture adsorption equilibrium favors ethane, whereas CO2 is a more mobile species because it can hop from one cage of DDR zeolite to the adjacent cage much more frequently. In this case, a factor 1,000 times faster than ethane. So the diffusion selectivity overrides the adsorption selectivity, which favors ethane. The diffusion selectivity favors CO2, and overall the separation is driven by diffusional considerations. So we note the first common feature of synergistic and antisynergistic separations is that the more mobile component experiences a pronounced overshoot in its equilibration process. To model this overshoot, we need to adopt the Maxwell-Stefan diffusion formulation for the intra-crystalline diffusion fluxes. This is shown here. And the driving forces in the Maxwell-Stefan formulation is the gradients in the chemical potentials. The gradients of the chemical potentials can be related to the gradients of the molar loadings via a two-dimensional matrix of thermodynamic correction factors. Indeed, the off-diagonal elements gamma 12 and gamma 21 are the main reasons for the overshoots. If we ignore these cross coefficients and assert that these are zero, then the overshoots disappear, and they are shown by these dashed lines. The continuous solid lines are the predictions based on the Maxwell-Stefan diffusion coefficients, taking Maxwell-Stefan diffusion equations, taking due account of thermodynamic coupling. Ignore thermodynamic coupling and there are no overshoots. So you may ignore thermodynamic coupling at your own peril. There is another feature of synergistic and antisynergistic separations, and that is shown in the next slide, where we plot the experimental data on the component loadings one against the other. In this slide, I plot the four sets of experimental data in composition space. The x-axis is the molar loading of the tardier species, and the y-axis represents the molar loading of the more mobile component. We note that the equilibration process follows a serpentine trajectory to equilibrium in all four cases. This is time t is 0, the start of the uptake process, and at the end of the equilibration, we have followed a serpentine trajectory in all four cases. The serpentine trajectory is bounded by these two straight lines the red line and the blue line. The red line represents the fast eigenvector and the blue line represents the slow eigenvector. The details of these calculations are presented in my precision chemistry paper, which is online since a couple of days. This is an American Chemical Society publication. The scenic paths taken by synergistic and antisynergistic kinetic separations reminds me of the poem by William Wordsworth. I wandered lonely as a cloud that floats on high o'er vales and hills, when all at once I saw a crowd, a host of golden daffodils. There are distinct advantages of following the scenic route to equilibrium, because you might then feast on a host of golden daffodils. And the advantages of such equilibration paths is outlined in my 2023 paper. I invite you to have a close look at it.